So it's very, very easy because you don't look at numbers then. You just see the pic and you react. It's very simple. So I'll try to make it as simple as possible. So I'll cover two topics in next 30-35 minutes. Pulmonary graphics I'll try to cover in 20-25 minutes. And last 10 minutes I'll take a small presentation on acute deterioration on a ventilated BB. Okay. So I would be happy if somebody has any queries, you can put up in the chat box and we can take it up later. So pulmonary graphics, just to see what is the objective of our presentation, will identify what is the graphic display on each and every ventilator. Normally, every ventilator nowadays has graphics. So describe how to use graphics more appropriately. That's very important to understand the graphic and see which graphic is useful in which scenario. That's very important. You cannot use all types of graphics in all scenarios. Okay. And appropriately how to troubleshoot. Pick up early and react. That's what we want. It should be clinically useful. So at the end of this talk, you should have some take-home messages and go back and see the ventilator before attending the workshop also, see what you're seeing. Okay, and we'll discuss all this in the workstations also when you meet in Lucknow. So basically, if you start off, there are two types of graphics. So just to divide them, one is scalar graphics, which is against time. So there is pressure against time, flow against time, and volume against time. We'll discuss each and everything in detail. The other one is loop, where two parameters, pressure or volume, are placed against each other, x and y axis. Or the second loop is flow or volume loop. So scalar loop, everything is displayed as per time sequence, and loop is two parameters are displayed, x and y axis, against each other. Okay, so two types of graphics, scalars and loops. So basically we'll start off with scalar graphics. As already discussed, there are three types of scalar graphics here: pressure time, flow time, and volume time. Let's see how each and everything looks, how each graph looks. Okay, so whenever you switch on a ventilator, you see the graphic. This is the most common thing which is seen. If I go through this, so this is a pressure time. So x-axis will be time, y will be pressure here. And mind you, pressure will always be slightly above the baseline. This is what is called a PWP. We'll discuss again. And there'll be a ascending thing, slightly flattening and descending curve. Again, there'll be a phase of no ventilation or minimal ventilation, and then there'll be low. This is pressure time scalar graphic. The other one is flow time. X-axis will be time, y will be flow. Okay. There'll be a inspiratory limb, there'll be expiratory limb. We'll discuss all this. The third one is time and volume. So this is volume. Okay, so pressure, flow, and volume depicted against time. So this is against a scale of time, scalar graphics. So moving on to the first scalar graphic, this is volume time. So as displayed, x-axis will be time, y-axis will be volume, always remember. Okay, and it will be a loop. It will the graph will start off from the zero, the baseline. It will go up and it will come down. So just to understand the point where there is peak from the onset, this is the I time, inspiratory time. And from this point to the whole end of the cycle will be an expiratory time. So this part is inspiration. This whole part is expiration. Okay. So I time and E time, this whole complete, this thing, this is E time, not this. Okay. And the volume which is delivered at the peak, that is a tidal volume. Okay, so here we can see the tidal volume delivered, and here we see the time. Okay, inspiration and expiration. Okay, so next very important scalar graphic is pressure time. Again, as told, time will be here in seconds, pressure in centimeter of water in y-axis. As already depicted, unlike pressure time scalar graphic, volume time pressure graphic, pressure, this thing will always start from above the baseline. And this gap is the PWP, positive and expiratory pressure. It should not start from here. Okay. So to start from here, it will go up in ascending manner. It will go down in a descending manner. Similar to volume time curve, this thing is inspiration, TI, And from this point, from peak to the complete expiration is the TE. Okay, so again, in the time uh, graph, we can see this is Ti and this is Te. In the pressure y-axis, we can see this is the pressure, which is just above the baseline. And the peak pressure which is being delivered is the PIP. Okay. In the volume time curve, it was the tidal volume. Here, because y-axis indicates pressure, this is the PIP. So this is the PIP, peak inspiratory pressure, and this is the PEEP, which is at the end of the expiration. Okay. And the third one is the flow time curve. And flow time curve, unlike pressure and time, will have a positive curve and the negative curve. So anything above the positive curve is the inspiration, which comes down and again goes in such a manner is the expiration. X will be the times in seconds. Y-axis will be the flow in liter per minute. Almost this is a standard. Some machines will have the lower side there will be inspiration, upper side will be expiration. But by default, Indian machines will have inspiration on the upper side and expiration on the lower side. Okay. So again, I time here will be this completely. This is Ti, and this whole from this point to this end is the Te. Okay. So I time and E time on the x-axis, and this maximum flow is the peak inspiratory flow rate, and the maximum flow on the expiration is the peak expiratory flow rate. So you have to see the curve or loop which you are seeing. So in flow, it will be a peak inspiratory flow rate and the peak expiratory flow rate. In the volume loop, it will be a volume graphic, it will be a tidal volume. In the pressure graphic, it will be PIP and PWP. And in the x-axis, always it will be a time. Okay. So flow time, you can use multiple, it will help you a lot. Just by seeing flow time curve, it's quite useful. First of all, it will identify the mode of ventilation. Let's see how it does. So this is a flow time curve where flow, inspiration, and then expiration. So by default, if you are dealing with a volume ventilation, if you're doing volume ventilation for a baby, the inspiratory part in the flow time curve will be a square shaped one. Okay. In a pressure ventilation, which you can normally do in SIMV or a normal PTV without volume ventilation, the inspiration part, the flow curve will be purely sine waved. Okay, it will not be a square wave. It might be ascending, descending, whatever, but it will be a sine wave. And in volume ventilation, the flow time will be purely square wave. Okay, but just looking at flow time graphic, you can say whether you're dealing with a pressure ventilation or a volume ventilation. Okay. Second, very important is you can identify high airway resistance. Let's see how it does. So normally, if you see, the flow should go up, then it descending inspiration. So this is an ascending inspiration. This is a descending inspiratory part. This is a descending expiration part and the ascending expiration part. Okay. So whenever there is resistance against flow, usually it impacts the expiration first. Okay. So there will be the peak flow. As I told you, this is the peak expiratory flow rate. The peak expiratory flow rate will go down whenever there is expiratory resistance in the airways. Okay. Maybe it's intrathoracic or extrathoracic. And the time to end the expiration will be prolonged. Okay. Here we can see it is very steep. But the moment there is increased resistance to expiration, the time will be prolonged. Okay, there will be two changes here. So peak expiratory and flow rate will be less, and the expiratory time will get prolonged. Okay, just by looking at this, you can say there's some resistance. Probably if you auscultate and if you see there is a bronchospasm, there is a sign of wheezing or bronchospasm, you bronchodilate, you use an bronchodilation, and then you see the change in the flow time curve. And you can see the curve might change back from this to this. Okay. So just by looking at this curves, you can easily say whether you have intervened, whether the intervention has worked or not. So third most important utility of flow time graphic is gas trapping. It's very, very important. I'll show how it does. So normally flow should come here and it should go back to the baseline. Okay, should touch this baseline. Suppose you see a graph where inspiration is okay, but expiration actually ends suddenly here and then inspiration starts. If the inspiration starts below the baseline and the expiration doesn't end or doesn't touch the baseline, that means there is gas air trapping. Okay, you can see the other forms also in other loops also, but flow time curve is the best loop to see air trapping. So if the expiration is not ending and not touching the baseline, its inspiration starts below the baseline, that means there is a gas trapping. Okay. Fourth most important is how to see whether inspirated time is adequate or not. Flow time is the best loop or graphic to see whether your inspirated time is adequate or not. So blindly, if you set every baby at 0.45 or 0.4 and 0.3, that doesn't work. You have to use graphics to say whether you're dealing with in an appropriate manner. So let's see how this graph works. So if I set my T inspiration as 0.3 second, just look at the pressure time graphic. It goes this way. If I see the flow time graphic, it suddenly ends here. So it goes up, it ends suddenly here. If you go back, it should end in a very smooth manner. Okay. But in our curve, this goes very suddenly downwards. Okay. So probably the inspiration is not being delivered appropriately. Probably either there is a blockade, there is a leak, or something is wrong where inspiration is not appropriate. So suppose I change my inspirated time to 0.45 second. Let's see what happens. The flow actually goes down very perfectly. The way we see it goes up, descending, ends, doesn't end very appropriately. Tidal volume, if you see practically, there's not much difference here, but tidal volume here will be like 20, around 20. Here it will go around 25 with the same pressure. With the same pressure, changing the I time, the flow time curve actually corrects itself, and there will be increased tidal volume delivery because you're giving more inspirated time for the machine to equilibrate with the PB. Okay. So I time is very important. And sometimes I'm not shown here. Suppose you give a very prolonged I time. Suppose you give a I time of 0.6 seconds. It will end here. It will stay for some time and then expiration starts. So that is an inspiratory hold, which is usually a zero ventilation time, wastage of time. So ideally it should end here and expiration should start. This is an ideal condition. Okay. So this, remember this loop, and this is the ideal loop we should have. This will decide I time. Okay. So last utility of flow and time, flow versus time graphic is termination sensitivity. So normally, if you see the flow time curve is usually like used in pressure support ventilation. So suppose I set a termination sensitivity almost of 15%. What does that mean? Whenever the flow is 15% of the peak flow, suppose I say the peak flow is 10 liters per minute. The net tidal volume, if it reaches 1.5 liters per minute, it will go into expiration. It will not wait for the complete I time. So here, it's not a time cycled, but a flow cycled ventilation. The cycling will occur not because of fixed time duration, but it will be a flow cycle. Normally, you can set up in any mode, but usually by default, PSV mode is flow cycle by default. Again, I'll repeat it. Termination sensitivity is, suppose I set a termination sensitivity of 25%. That means 25% of the peak flow, whenever it reaches that 25% of the peak flow, it will switch to exhalation mode. Okay. It will not allow further inspiration to end. Okay. So that reduces the duration of inspiratory hold, minimal ventilation period, and the cycling is very smooth and there is proper ventilation. Okay. So these are the few utilities of flow time loop. Again, I'll revise it. you can identify modes of ventilation, you can identify resistance, you can identify gas trapping, you can decide inspiratory time and optimize it, and the last of all is termination sensitivity. Okay. So we'll move on to the loops now. So first, very important and very commonly used loop is the PV loop, or otherwise called as compliance loop. So what is the most important determinant of PV loop? How can you use it to determine optimal PEEP? Optimizing PEEP, you can use a PV loop. Let's see how we can do that. So before that, I'll just go through the components of PV loop. So this is x-axis will be the pressure, y-axis will be the volume. Pressure in centimeter of water, volume in ml. So this is wrongly depicted. Normally it starts off from somewhere here. This is the inspiratory curve. This is the expiratory curve. Okay. And the maximum pressure which is being delivered here is the PIP. And somewhere here is the PWP. I'll show in other graphics. That maximum volume delivered here is the tidal volume. So this is the point of tidal volume. This is the point of PIP, and here somewhere is the PWP. Okay, we'll again discuss. We'll see how it works. So as talking about PWP, just go through this. So this is PWP, inspiration and expiration, and this is the PIP, and this is the point which from where inspiration starts is the PWP. Okay. So how to decide optimal PEEP? So just go through the two loops here. So this loop is almost flattened. Okay. So I forgot to mention one important point here. So PV loop, the curve, the inclination actually says about compliance. The tidal volume delivered with respect to pressure which is being used is the compliance. And this angle or inclination tells you about compliance. So more upright it is, it's better for the baby. Compliance is better. The more flattened the curve is, the compliance is low. Okay. So we'll use this in further curves, further loops. So again, going back, optimal PEEP, how do you decide? This loop looks flattened to me. This loop should have been this direction rather than this direction. Okay. So this is almost like a 30 degree curve from the baseline. So if you see properly, the pressure which is being increased from this to this, there is no change in tidal volume. So as told, in y-axis, there is tidal volume. There is no change in tidal volume if you increase the pressure from this point to this point. From here onwards, actually, volume increases. So this is a wastage of pressure. Probably you need to increase PEEP from this point to this point, because there is no difference in tidal volume. You increase the pressure from this point to this. So if you start your ventilation probably around this point, probably you will get better compliance. You will get more tidal volume for the same pressure. Okay. And similarly, the loop will come down. Suppose I change my PWP from 2 to 5, 6 here. You can see the change in the tidal volume. Okay. For the same pressure, PIP here is 20, tidal volume delivered is 7 ml. For the same PIP, almost 21, I get a tidal volume of 10 ml. So by increasing the PWP, you get more tidal volume with the same pressure, PIP. Okay. So PWP again is a very important parameter to change or increase the map also. Okay. So using a PV loop or compliance curve, you can actually optimize your PEEP. Ideally, you should not have this such type of loop. The loop should be more of 45 degree angle. It should be most inclined to 45 degrees. Okay. And there should be immediate change in tidal volume the moment pressure rises. Okay. So this is a way to optimize the PWP. And very important is this is by default called as compliance curve or compliance loop. So you can see how compliance works, how change in compliance happens using this loop. Okay, let's see. So there are 3 loops here. The one in the green is almost like an ideal compliance curve, 45 degree angle. The one here is slightly flattened, and here is slightly going up. But any day I would accept green and yellow one. The one which is in the red is slightly flattened. So with the same PIP, you get less tidal volume in the pink loop, slightly better tidal volume in the yellow and the green one. So ideally is green, and yellow is still acceptable. Okay. But you should not have low flattened curves. So that flattened curves implies low compliance now. Green and yellow implies better compliance. Okay. So just by looking at this pics, you can see whether you are dealing with a poorly compliant lungs or a well compliant lung. Okay. Just very important clinical utility of compliance curve is response to surfactant. Suppose you have intubated a baby and you're giving surfactant, and then you see the response. This is the best. Okay. So just you can see the curve is flattened here, almost a 20-25 degree angle. With the PIP of around 24, you're getting a tidal volume of 6 liters per minute, 6 ml. Okay. But the moment you give surfactant after an hour, if you see, sometimes in minutes also, or sometimes in hours, with the same pressure, the tidal volume delivered is 12, almost doubles up, and the loop actually goes up. Okay. So it should change from 30 degree to 45 degree angle, and the compliance should improve, and you should get more tidal volume with the same pressure. Okay. So last and very important is for PV loop is to determine whether you are giving high PIP. Let's see how it does. So, sorry, think mistake. Yeah, sorry. So over distension, some slides on happens there. So pressure on the x-axis, volume on the y-axis. So this is the inspiratory end part of the loop, and here comes the beaking. So with this change in pressure from this point to this point, there is no change in tidal volume. That means this is the extra pressure being delivered. Okay, so this is called beaking, or whatever, duct big, anything. There are multiple names to it, but this is more of a beaking which is seen, and this is a wastage of pressure being delivered. Ideally, you should end up with PIP at this level, because there is no change in tidal volume after this increase in pressure. Okay, so this is over distension. Okay, and there's something called C20 by C. Most of the machines will show you what is C20 by C. So just I'll go through that, this thing. So C20 by C is ratio of compliance in the last 20% of the loop compared to the compliance of the whole loop. What does that mean? So if I draw a line on this part and I want to see the compliance of this part, 20% of the loop, and I compare the compliance of the whole loop, the ratio will be called as C20 by C. Ideally, we want the compliance of last 20 part of the loop to be equal to the other part. So it should be 1, or it should be not more than 1, but at least 1. If the C20 by C ratio in your machine shows up value should to be less than 1, and significantly if less than 0.8, that means you're dealing with a over distension or a beaking, or you are giving a very high PIP. Okay, so C20 by C in your machine should be always 1 or more. Okay, so last part would be to determine whether we are giving adequate flow or not. Okay, so if there is appropriate flow, the curve will look this way. Okay, if there is inappropriate flow, there is less flow during inspiration, there'll be air hunger. There'll be somebody has eaten the loop. Okay, suppose there is inadequate flow, baby needs 7-8 liters per minute, and you're giving 3-4 liters per minute, which some ventilators you can manipulate. There'll be a figure of 8 or air hunger loop in a PV law. So ideally, it should start off on this point and go end this point, but here it will be a figure of 8 appearance. If there is a figure of 8 appearance in PV loop, you need to increase the flow. Okay, that shows. Okay, so you can know the compliance, you can know the after surfactant effect, you can know the air hunger or the flow rate, you can know the optimal PIP, you can know over distension using a PV. Okay. So final graphic from our point would be flow volume loop, and flow volume loop also has its own utility. I'll just go through that and discuss how flow volume loop works. But first of all, just to complete that, we should know the part of that. Already we have discussed the initial part also. So peak inspiratory flow rate, this is the peak inspiratory flow rate. Then it will end of year and then expiration with peak expiratory flow rate at this point. Okay, so inspiration will be on the upper side and expiration will be the lower side. The volume delivered here will be the tidal volume, which will end here. And this is the FRC. Okay, so flow volume loop, most important is air leak. Okay, so normally flow volume loop looks like this: inspiration and expiration. If the expiration doesn't end here, but ends up here, this is the leak in volume. Okay, so volume should end here, but the whole volume is not being delivered and there is some leak here. Okay, so again, I'll show the loop again. So inspiration and the expiration ends not at this point, but prior to that. This is air leak. On the contrary, air trapping. We had seen flow time loop, if you graphic, if you remembered earlier. Inspiration will go up and expiration will end prior to the line. Flow time will show air trapping. In the flow volume loop, flow trapping will look like this. Inspiration and expiration will not end here, but will end here somewhere. Yeah, this is the flow doesn't return to baseline. That is the air trapping. Okay. So if it ends here, this is air leak. If it ends here, this is air trapping. Okay. Flow volume loop will again show resistance for expiration as discussed in flow time graphic also. I'll show examples of that. So inspiration here, ideally it should, curve should move this way. But if you see, the peak expiratory flow rate will come down and there will be scooped out pattern or ski slope pattern. Okay, so this will be there will be indentation in the expiration. The PFR will be reduced and there will be a scooped out pattern. Okay, there will be a indentation in the loop. That means there is some resistance in the air. Okay, there are various patterns of determining resistance, intrathoracic, extrathoracic, and all that. I'll not go into detail of that. And last, very important utility of flow volume loop is to determine secretions. So let's see how it looks. Simple. The moment you see these indentations in an expiratory part of the flow volume loop, you should know that you need to do a suctioning. Okay, it's very, very classic. Okay, so very useful flow volume loop. So looking at different loops and graphics, you can almost finalize the common conditions you can deal and act appropriately immediately. So last part of my thinking, just to identify, just a question for all. Okay, just a second. So identify this. If anybody can put in the chat box also, it will be useful. Okay, so I'll just, this is a pressure volume loop, compliance curve, PWP here. It goes up and it ends suddenly here, doesn't come down. This is a dotted line, but actually doesn't, it ends here. Okay. Similarly, in same PB, flow volume curve, it will end here. So what is this? Air leak. Somebody has written air trapping. Again, we can discuss in the actual workstations, but air trapping is different. Okay. So just to summarize what I have shown here, PV loop, it will go up and suddenly it will fall flattened. Okay. In the flow volume loop, it will end here. And if you see the volume time graphic, it will not come down to baseline. It will end somewhere here. There will be a gap. Again, there is an air leak. Okay. In air trapping, it will be different. Okay, so flow volume will actually end here. Okay. And in the flow time curve, it will end somewhere here. Okay. I hope you've attended the watchful when I told you previous sessions, previous slides. Okay. So to conclude, pulmonary reference is very, very important. If you are quite keep it very simple and try to identify which loop you want to see for which condition. And it's very simple as ECG for heart or ABG for ventilation. Just by watching, you can change a lot and you can do immediate action. It doesn't take much time. It's very, it doesn't, it's available easily on every ventilator. Okay. So I hope